Okay, so now we have Marco Campion from University of Verona. He will be talking about partial incompleteness in abstract interpretation. Go ahead.
Yeah, sure. I can click it here. Okay. Hello. Okay. Hello, everyone. Thanks for the introduction. And this is a joint work with Mila, Dalla, Preda, and Roberto Giacobazzi. So in abstract interpretation has abstractions which transform undecidable program properties into decidable approximations. Moreover, abstract interpretation is sound. So this means that the result of our abstract interpretation over-approximates the result of our concrete operator that we want to approximate. And when these two results does not coincide, we have, in this case, imprecision, also called incompleteness. Conversely, we have completeness when these two last results are equal. So in this case, completeness represents an optimal configuration where we have no imprecision in the abstract domain that we have chosen. So the problem here is when abstract interpretation is used for program analysis, then completeness, unfortunately, is hard or even impossible to achieve. Also, completeness is an issue. And we can also expect different level of incompleteness. So for example, consider this program. If we want to know the value of variable x at the end of the program, and we want to analyze it in the interval abstract domain, then if we perform a collective semantics, we get the expected result with the interval with one element. And when we have the abstract semantics, in this case, we have we cannot show here, but we have the interval 0, 100, while with the best correct approximation gives us as a result an interval of 0, 10. So in the last two examples the last two analyses are incomplete in this case. Moreover, we have different level of imprecision. So the question now is, can we measure this difference? So can we define a bound of imprecision of our program analysis? So in order to answer this question, we start by defining some kind of matrix that must respect the underlying structure of our abstract domain. So we say that a distance over the elements of our abstract domain is a quasi-metric A-compatible if it satisfies these four axioms. So namely, if it is a decidable predicate, if it returns 0 for the same two elements, if it respects the partial order relation on the abstract domain, and finally, if it respects the triangle inequality only along chains. So we say that giving a pair of abstract domain and quasi-metric A-compatible, then we say that this pair is called an abstract quasi-metric space. So as a simple example, we define the weighted path length over the abstract domain over abstract domains that treat abstract domains as directed graphs, where each head has a weight. So the result of this distance is just the minimum path length between two elements. So for example, in the sign abstract domain, we have that the distance between the bottom and the top element is 3, while the converse is undefined. While in the interval abstract domain, we have that the distance between, for example, the interval 1.00 and the interval -1, 2 is 3. And this encodes the number of more elements that the second interval has with respect to the first one. So in this case, also the distance is undefined for two intervals such that the intersection is the empty set. So we can now define a new property which weakens the completeness property in abstract interpretation that we call the epsilon partial completeness property. So we say that an abstract interpretation is epsilon partial complete for an input x when the result of the concrete operator f abstracted in the abstract domain is epsilon close to our abstract interpretation f sharp, namely the distance is at most epsilon in this case. So in program analysis, we can encode this result by admitting in epsilon an epsilon amount of false alarms. And here, so the imprecision is measured by a quasi-metric A-compatible. So we now deepen our study in program analysis. So we start by defining our toy language as regular commands. We define our concrete semantics as the collecting the notational program semantics over the power set of the set of stores. Then before we define the abstract semantics, we define which abstraction we are interested in for the program analysis. So we say that we will consider only strict recursive or trivial abstract domain of stores. We say that an abstract domain of stores is recursive when the abstraction function is computable and the concretization function returns a recursive set, and also we need the partial order over the abstract domain to be decidable. Also, we will consider trivial abstraction of store, namely the identity abstraction and also abstract domains with the abstract domain with only the top element in this case. So we define the abstract semantics as by starting with the best correct approximation of basic commands and then by composing them. At the end, we get our abstract semantics, which is an over approximation of the concrete semantics, the collective semantics, and in the middle, we have the best correct approximation. So we given an abstract quasi-metric space in bold and an input S of stores, we call the epsilon partial completeness class of programs as the set of all possible programs, such that the result of our concrete semantics, so the abstraction of our collective semantics, is epsilon close to our program analysis. So this set of programs is an overset of the completeness class, because completeness requires no imprecision for every input, while we require an epsilon amount of imprecision just for the input S. And this is also an overset of the local completeness class, which requires completeness only on input S. So for example, by considering the example that I've shown in the introduction, then we have that in this case, this program is not in the 0 partial completeness class because it is not local complete to the input 2, 4, but it is in this case in the 100 partial completeness class. So this is because the result of the output of our abstract semantics over the program has 100 more elements with respect to the concrete execution in this case. Okay, so we want to answer a fundamental question. Can we define a program analysis which is epsilon partial complete for every possible programs? So in this case, when the abstract domain is the identity, then the answer, of course, is yes, because the result is that our properties holds for every possible program. But what about when our abstract domain is not trivial? Then in this case, the result depends strictly on the quasi-metric IA compatible that we have chosen. This is because if we say that our abstract quasi-metric space has a limited imprecision by epsilon, then in this case, for each element in our abstract domain, the distance between the bottom element and the A element is at maximum epsilon. So in this case, of course, there exists an epsilon such that this property corresponds to the whole class of programs. For example, if you consider the sign abstract domain, and if we set epsilon to 3, then we get that our program analysis is obviously is epsilon partial complete for all possible programs in this abstract domain. While we have unlimited imprecision when for each epsilon, so for each epsilon bound, there exists an element A in the abstract domain such that the distance, the quasi-metric distance between the bottom element and this element is strictly greater than epsilon. So we have proven a theorem such that it says that if the abstract domain is not trivial and satisfies the unlimited imprecision, then in this case, there always exists an epsilon partial incomplete program. So this means that there exists a program for which our upsilon analysis is imprecise by an amount strictly greater than epsilon in this case. This is because we can always define a program which is a composition of a non-terminating program and another program whose upsilon interpretation gives us as a result the recursive set A, so the element A. So the result of the concrete semantics in this case is undefined, so it's bottom because it's non-terminating, while the result of our program analysis is exactly A. So we can conclude that this program P it is not in the corresponding partial completeness class. So for example, the interval upstream domain together with the weighted path length satisfy this property of unlimited imprecision. So the second question we want to answer is, can we define an analysis verifier that takes as input a program analysis and a program and an input, and verifies our program analysis as bounded imprecision, so can answer either yes or no. And this is equivalent of asking if our program is in the corresponding partial completeness class. Then the answer here depends on our abstract quasimetric space, so on both the abstract domain and the quasimetric A-compatible that we have chosen. So we have that the first result is that if our abstract domain satisfies the ascending chain condition, then our property of programs is a recursively enumerable set. This means that we can at least answer yes to the question, but otherwise we don't know. So the proof corresponds to building an algorithm that just runs our program analysis and then collects in a dovetail fashion the results of the all terminating concrete semantic or the terminating execution over enumeration of our input set S, and then it starts collecting this by doing the results, so following a chain. So if at some point there exists some input Si such that the result is epsilon close to the result of our static analysis, then we can conclude yes. And this is because we are following an ascending chain, and our abstract domain satisfies the ascending chain condition. Conversely, if our abstract domain does not satisfy the ascending chain condition, then we can conclude that this property is not recursively enumerable. This set of programs is not recursively enumerable. Namely, this problem is undecidable. And this is a direct consequence of the infinite chains in our abstract domain. So can we answer the dual question, namely, can we prove if program analysis has not bounded imprecision? Then also in this case, the answer is no, because the problem is still undecidable. So this problem corresponds to the complemented class of partial completeness, epsilon partial completeness in this case. And this is because we need to answer the question about the non-termination, because if our program never terminates on S, on the input set S, then we need to know we need to know that the program is non-terminating before concluding that P is the corresponding epsilon partial incompleteness class. So this is undecidable. So this table summarizes the main results that we obtained for the partial completeness class property. And we have also direct implications, of course, on the local completeness class. So what now? We have two negative results. We know that we cannot define a program analysis which is always epsilon partial complete. And also, we cannot check if our program analysis in general has a bounded imprecision. So what we can do now is performing an error estimation of our program analysis. And we do so by defining a Hoare-like logic. So we define a tripole with a precondition, a program P, and a postcondition together with an epsilon bound. And we say that this tripole is true whenever the result of the execution of program P with input the precondition, the result in the abstract domain is epsilon close to the abstraction of the postcondition. So we are using, in this case, the epsilon bound together with the postcondition in the tripole. So we define a simple proof system for error estimation in this case, and we collect such that we collect in the post condition the error accumulating during program analysis. So for example, if we consider the sequential rule, in this case, this rule is very similar to the standard for logic, but it requires also another condition, which requires that the program P2, we need to know the distance between the actual execution of program P2 with input the output of P1, with input the precondition, and the result of the execution of P2 with input the postcondition of the first tripole. And in this case, we can consider as an over-approximation bound as the sum of the epsilon and eta bound. While for the join operation, we need to know what is the bound on deep precision applied when we perform the join between two elements that are epsilon close. So with our proof system, if you can deduce this tripole, namely the tripole where instead of the post condition, we set the post condition with the result of our abstract analysis, then we can conclude that our program is epsilon partial complete. So in this case, we have computed the distance between the concrete execution and our program analysis. While if we set the post condition as the result of the best correct approximation, we can know the bound of the imprecision induced only by our abstraction. And finally, if we perform a slight modification of the two rules assign and bool, then we can define a new proof system such that it is able to estimate the error also between the best correct approximation and our program analysis in this case, concluding the cycle of error estimation. So by concluding why it matters, so we start by saying that completeness is a hard or even impossible task in program analysis by abstract interpretation. Therefore, we define a new property which requires a bound level of imprecision. And we define a framework which provides ways to estimate analysis imprecision. So our goal was to help abstract interpretation designers to control error propagation. And we define a proof system which types analysis by the precision with regard to a program and its input. So this reasoning can be considered also as a dual way for quantifying the potency of code obfuscators. Thank you.
Thanks for a great talk. Questions from the audience? Okay, so there is question on air meet from Shuo Ding. Is it possible to generalize those computability results about imprecision to arbitrary program analyzers verifiers, including those not directly based on abstract interpretations?
Okay, that's a good question, and maybe yes. I don't know, but we focused our analysis on abstract interpretation because of the soundness property, but maybe yes. So we need to define another framework where to starting from in order to analyze the computational problem like this. This could be a good point for a future work.
Okay. Any other question? There is one new one on your meet from Long Pham. It may be interesting to extend your framework with probabilities.
Yeah.
Thoughts?
Yeah, this is what we are performing now actually. So by considering either probabilistic programs or some inputs to our program that is like a random distribution over the inputs. So yes.
Okay,
So I noticed in your definition of quasi-metrics, you use the rational numbers as opposed to reals. Is this a nod towards assuming that your state space is discrete, or do you have any kind of model for a continuous abstract state space?
Well, actually, we consider rational numbers. This is because we are considering abstract domains as a set of recursive sets. So in this case, we can think of the distances just like the height of the elements in the abstract domain. So we can just consider we can reduce the distances over just the rational number and not over the real numbers in this case. But we can also extend to other kind of maybe abstract domain that are not recursive, and maybe we can also extend the range of the bound of imprecision.
Any other questions? Not then I have actually a few questions from my own. So this kind of thing, do you have any way of defining for, let's say, relational domains?
No, actually, we just defined a simple metrics for the well-known sign and interval star domains. So actually, no. The answer is no. But we plan to do this for actually for Gala insertion-based abstract domain, abstract interpretation in this case.
Okay. So do you think like something like a volume can be?
Yeah, of course. Yeah, maybe also in the paper we have presented some very simple result of our measures. So by using like integrals or volume in order to measure some measurable set in this case, yeah.
So I was also thinking that something like this can serve as a proxy, or even if you cannot compute this measure exactly, you can compute a proxy measure which might not have the same guarantees, but still it kind of gives you an indication of if you are losing precision, and then you
Yeah.
can use it for maybe switching to a more precise analysis.
Yeah, that's yeah.
So I
Yeah,
was
you
also
you
thinking
get the
that
point.
one can also define this kind of measure to be kind of differentiable, like do like loss function in machine learning.
Yeah, that's true. That's true. We can extend also with this is a very good point. So it's interesting also to try to extend this framework for those arguments in this case. So yeah.
Sounds good. Thanks for the talk.
Thank you.
There's one more question. Because we have one more minute, so there's one more question on air meet.
Okay.
Is it possible from Chengpeng Wang, is it possible to estimate the density of the concrete states aggregated in the neighboring area in the abstract domain?
Okay. That's a difficult question because maybe we require some properties in order to be able to do that, maybe we require some properties on the concrete domains. So we can think of something, but yes, we can maybe change the framework in order to be able to apply measure directly on the concrete domain in this case, yeah.
Okay.
Thank you.
Then we can finally